And I would like to hand over the discussion to the moderator of the day, Professor Shubhi Sharkar. Thank you.
But where is the audience? Shouldn't have
want to
given a
discuss.
We can do a round break of
5-minute break is a bad idea because then, please come in. We are about to start the discussion. Thank you. Huh? So, Raman, you better turn your chair because I want you to see the screen as well. Didn't Dick come back from after lunch? Yeah. No, we didn't need another break now because we are already quite late. Giri, I'll show some slides. You might want to spread out a bit so you can crane your neck. I'm sorry, I didn't realize they would put the chairs back to back. Where is the, shall we start? Waiting for somebody. Is Tarun coming? He's in a meeting. Okay. All right, let's get going. So we've had a long meeting, and this is the final panel discussion, which is already 15 minutes late, but that's okay. We are told to discuss all the open questions and so on that were raised during the conference, but I looked at all the talk titles, which I've just put down here in an impressionistic manner. Longest title award goes to Dick at the top right corner. But obviously, you're not going to be able to discuss all the issues that were raised during the talks. And we have already had 2 or 3 discussions in the past few days, which ranged over some of the contentious points. So I thought maybe what would be useful if we could go away from this meeting with a few key takeaways. And some of the things that I see, both in this meeting and the previous one that we had last year, are some confusion in the community about what has been established and what is not. Some things are matters of opinion, but facts are sacred, and especially experimental facts. So with that in mind, I want to focus on, take the privilege of the moderator to instigate discussion on a few key points, and I will invite, as is my remit, as it says there, I'm allowed to ask you panelists to share your take, and then the discussion is open to the audience. So let's start with a point that has come up several times in our discussions, which is that we heard that many of you are prepared to sort of say, well, I don't really believe the supernova observations, I won't bet my house on it, if you like, but isn't dark energy established from CMB, a large-scale structure by itself? And so I'll like to show you something very quickly that Lyman had forgotten about, and if he's forgotten, then most of you would have forgotten also. So let's go with that. So So what I would like to say is that the formation of large-scale structure is like a scattering experiment. I do high-energy physics, and so everything to me is like a scattering experiment. So you have a beam. That beam is the inflationary or whatever source it is, density perturbations. And we don't actually know what this beam is. At CERN, we know what the beam is. We can tune it. Here, we assume that it is adiabatic. The isocurvature has been constrained to be small, but close to scale invariant. We know that the spectrum has to be close to scale invariant. We have known that since Harrison and Zeldovich long before inflation. We don't know what the target is. It is dark matter, but we don't know its composition. We don't know if it is interacting. We take it to be cold and collisionless, and a small sprinkling of baryonic matter. And we don't know what the detector is. The detector in this case is the whole universe. The products of the interaction between the fluctuations and the matter is described by a transfer function, but then we see the outcome in terms of things on the sky, and we model it by a cosmology with some parameters, right? So far, I think this is uncontentious. Now, the point I want to simply make is that the signal that we observe in multiple ways, many things can be added to that list, not just anisotropy and clustering and now weak lensing, CMB lensing in particular, but we really can scan at most about 8 to 10 E-folds of inflation. This will increase, of course, with the intensity mapping that is due to come, but currently it's about 8 E-folds. This we all know. Hopefully, I hope I live that long, but yes, all that is there in the future. But my point is simply that we have three unknowns, and what we see is their convolution in multiple ways, right? So we all know this. So we can't uniquely determine the properties of the detector from the unknown beam and target. We have to make some assumptions, some priors, then we determine the others. This is necessarily a convoluted problem. Now, these priors that you adopt are all reasonable, but let's not forget that this is necessarily a convolved problem. You can't just separately identify the beam, the target, the detector, and observe them one by one. So I'm going to show you, contrary to your belief, Lyman, that you can actually match exactly the same CMB and large-scale structured data without lambda. And so the answer to that question, any question at the end of a title means the answer is no, and this is true, right? So here is a deconvolution of the primordial spectrum from various data sources, from the CMB here, both ground-based and satellites, from galaxy surveys, from weak lensing, Lyman alpha, etc. Now, of course, your first thought might be, how do you deconvolve? It's an ill-conditioned problem. It's sensitive to your, whether you want precision or you want to minimize errors, etc. There's noise that increases. This is a technique called Tikhonov regularization, which is used to deconvolve images taken from aircraft or satellites. So Mr. Tikhonov was a hero of the Soviet Union because he showed you how you can take a blurry picture, and then using this technique, you see an airfield or a battleship or whatever. Now here we see this, and all these wiggles in the spectrum correspond to actual features in the data. So people who work on the CMB will know that there is a glitch at L of 26. That's what gives you that feature. It's not very significant. It's all 3 sigma. But my point is that we can do this exercise, and what is normally assumed as the prior is the dashed line. That's the line whose slope is being debated here in Paris as to whether it's 0.9684 or 0.9682 or whatever. But my point is that actually, although it's quite consistent with the data, it does not uniquely determine the primordial spectrum. The primordial spectrum is anywhere in that band, given this data. And the corresponding fit to the data from that spectrum by construction, because I deconvoluted the data to get that, is perfect. I can fit any data by choosing an appropriate primordial spectrum and the right parameters, and you see the fits are all pretty good. So the inferred cosmological parameters are, however, very different if there are spectral features. And to illustrate how different they can be, I show you an example. So this is the reconstruction assuming lambda CDM, and this is the reconstruction assuming Einstein de Sitter. And Subodh showed this in his talk yesterday. You have a more pronounced dip, and you have a higher rise here, but If I just showed you these two spectra and took away those labels, you would not have any problem if I told you they were deconvolved from the data. And indeed, both of these give an equally good chi-square for the fit to the CMB and to the TE spectrum. Okay? The difference between these two is that this has no lambda, and therefore, as has been known since the 90s, you'll get too much power on small scales for a CDM model only. How do you cure that? You can cure that by adding neutrinos. And if you add 3 neutrinos, degenerate, they would be degenerate if their mass is more than 0.1 eV, and these are 0.5 eV. And this exercise, as you can see, was actually done some time ago, in about 9 years ago. But you could get a fit to the data and suppress the power sufficiently to match the SDSS data at the time on luminous red galaxies by including neutrinos. Then, of course, you say, what about the cluster baryon fraction? Well, in this model, the baryon density is actually higher. It's 10% rather than 5% as it is in the normal cosmology. So the baryon fraction in clusters is predicted to be 11%, and in fact, it's perfectly consistent with the data as far as I know. Now, the clincher that came later was this evidence for dark energy from the CMB using CMB lensing. And here is the paper that Lyman mentioned, which I think there you are, which claimed that you could get the evidence from CMB alone. And when I spoke to Blake Sherwin, who came and talked about it at Oxford, I gave him our fit to the Einstein de Sitter fit with neutrinos. And the red line is our model. The blue line is lambda CDM. And the data at that time, this is what, 2011, was like that, big error bars, right? So now I know you have much smaller error bars. You have measured it a lot better. But my point is, this is a proof of principle. What you're measuring is an integral from here to the last scattering surface of the growth of structure. As long as I can match that in my model, you will get the same result on the sky. So these people, in fact, were nice enough to, they published that in PRL, but they did add a note to their archive listing in the version 3. Our constraints do not apply to models with non-power law, primordial power spectra, and so on. So that's my point, that you can't make an unqualified statement about lambda having been established from CMB and large-scale structure alone. It has been if the primordial power spectrum is a power law. Do we know that for sure? You know, this is the point, that we can't actually make a value-free or prior-free assertion to that extent. Of course, you can then ask, have these 0.5 eV neutrinos been found? So, okay, at this point, I should stop talking. So, Lyman, how do you, this is my elaborate answer to the point you raised. So, how do you respond to this?
Okay, so there are 3 points.
Yes.
First is the data are, as you said, much.
I would hope so. I would hope. I hope you have been busy in the intervening 14 years.
So there are 15. Yeah. So there are 15 years of data.
Yes.
And there are multiple experiments that are measuring the lensing to huge accuracy.
Yeah.
And I was trying to think if we ran the case. I'm sure we did somewhere. I don't know if it made it into the papers of letting omega k go, putting in a massive neutrino, and all the other parameters. And I can't remember specifically, but I bet it works out just fine.
Yes.
And you find a lambda, because there's so much, there's also information on the acceleration, right? Because the kernel is at redshift of 2, and lambda dominates starts to dominate at redshift of 10. Okay, so that's one. The data have improved incredibly since then, and so this exercise needs to be run. Okay, the second thing is, in that example, you were saying, so we just discussed a while ago, you are predicting the particle.
Yes, neutrino.
Absolutely.
Massive neutrino.
And so the Katrina limits, right, up to 90% confidence, is for the electron, so 0.45. So, and we know from the mass splitting, it can be the maximum can be 0.55.
Yeah. So this was an exercise we did with 0.5. I can tune it.
But it's okay. You're predicting a particle, which is a big thing.
Yeah.
I mean, that should be the title of your paper. We predict the particle.
It should have lambda, yeah.
That's the bottom
Well,
line.
sorry,
And so you can be falsified if
I
no
mean,
one
the
finds that
particle we know exists. We are predicting a mass.
you're
for the
predicting the
particle.
mass, exactly.
Okay, all right. No,
Right.
so anyway,
You're predicting the mass.
This was my proof of principle that often.
Yeah.
So actually, can I have a show of hands? How many people here knew that you can fit CMB, a large-scale structure, without lambda, just as well?
No, not today.
I actually disagree.
Okay, please, yeah. Sorry,
So
Mike.
we made this point a long time ago, of course, as we often have, but nobody listens. You're fooling around with zeta, and one of the most profound things with the microwave background is the shift of the polarization peaks.
Yes.
And so if you start to fool around,
Yeah.
you start to fool around with the structural issue.
Well, there is a
Well, no,
team.
but you're doing it as a power law.
Yeah.
But if you start to make it a structural issue where you have a lot of configuration, then you're going to blow that beautiful relationship of coherence. No, I'm not talking about TE.
No, you're talking about the
I'm talking
relationship
about-
with
I'm
Oh, you mean the anti-correlation? Is that what you're talking about?
I'm
On-
talking about the polarization spectrum
Yeah.
relative to the T spectrum.
Yeah. So you-
So it's, so, you know.
yeah.
one
Well,
has
that's
to
what
be
is shown
like
here,
that.
and that's the anti-correlation on super horizon scales. It's there.
No, I'm not talking about that. I'm talking about a much higher L's.
Oh,
where-
at
where-
higher
Where
L's.
you're oscillating,
Okay,
and you're
okay.
explicitly looking at, I mean, you know, the thing that has emerged is the absolute brilliance of E, and why are we even looking at T anymore, is more or less what's happened. in the
Strongest
micro-
signal.
No, the E is unbelievable.
You can recover the parameters
Huh.
to just
Totally,
about blank
yeah.
accuracy with just EE.
Okay.
Yeah.
Okay. All right. That's good.
And the point I'm trying to make is that it's this remarkable structure that at the moment doesn't support putting in a lot of structure in zeta. Of course, we're trying to do it. The other thing that I would like to know more about, but not necessarily right now, I have never run across the Tikhonov method. And what's weird to me is that you have no regularization at all on the allowed frequencies.
Well, we have regularizations is hidden behind that banner. It is lambda of 100. We did it with various values of this regulatory parameter. So you want a compromise between amplifying noise and not killing features. And you regulate it to the point where you have a optimal compromise between the two. Right? So you obviously...
Yeah, well, it seems to me that
Yeah.
you didn't choose the right compromise here.
Well, this is the one where we are actually at the turning point between the two curves. In fact, this came up in somebody else's talk as well. I can't remember whose
Anyway,
talk. Yeah.
that is not
Yeah.
the significant point here. The significant point is that the combination of TT and EE in particular gives you a very stringent, and you could probably beat those two up, and we do, right? You say, is TT result in agreement with EE, and then TE just adds extra ingredients to it. And so what you can do is make spaces where you have things that you derive from one, things that you derive from another, and they have to be the same because it's the same stuff. And it's a very interesting.
No, I
way to
agree
do
that it
comparisons.
can be done. Well, I don't want to make sociological remarks here, but
I have a question,
Please.
just for my
Yeah.
clarification, but also for the rest of the audience. You mentioned the Einstein de Sitter
Yes,
before,
yeah.
with neutrinos.
yes.
So, but where is that make it omega m equal to 1?
That's right, omega m is 1.
Yeah, but made
Yeah.
of what?
Made of what? We don't know. This is a fit with this is a parameter in the fit.
Just a much larger
Yeah.
amount
So
of dark matter.
how do you infer? You infer your omega matter, etc., all from observations anyway. The same observations.
yeah, okay, yeah.
You always do it in the context of a model. That's my point.
Yeah.
So
Just
in
to
this
clarify,
model,
yeah,
if I were to interpret the data, so for the omega matter equal to 1, actually it's 0.9. 10% has to be neutrinos. In fact, 0.8, because 10% is baryons,
So in
10% is
terms
neutrinos.
of parameters, the four is you have the same
0.8.
number.
It's 0.8.
No, the numbers of parameters that you have in the model, you add neutrinos.
We add neutrinos, that's
but
it.
you take away lambda, so the
Correct.
number of parameters is the same.
The chi-square is the same, when we add one parameter, then you have to pay a price for that in terms of you should get a better chi-square, at least twice the number of parameters you have. Yeah, we have checked all that. So according to the information criteria, you're better.
You have lots more parameters. You have
No.
all these wiggles and stuff.
Oh, yeah, so that's the thing. The wiggles are all generated in a model where you suddenly have a certain jump in the mass of the inflaton. All those oscillations in the spectrum are all analytically fitted. That's it. So you just have a mass jump and a position. You choose it to happen. It is tuned. It is tuned to give you a feature at the scale where it is cosmologically relevant. No, I'm not. The point I'm making is that some people have the point of view that I don't care about the underlying physics. Don't tell me that lambda is unnatural or whatever. I believe the data. Okay? So I'm trying to show you, you can actually match the data. That alone is not enough. Yeah.
Those data.
Those data.
Probably cannot these
Yeah.
days.
Yeah. Okay.
Which is the other point. I mean, these data are incredibly restrictive.
Indeed.
Incredibly precise. And they're I love going after anomalies. But there are multiple groups doing this.
Indeed.
Like, it's not one or the other. This is multiple people in
Yes.
cross-check and phase. They're incredibly constraining. And as we've talked about a bunch, and lensing as well. And so here I'll make, and again, I'm such a fan of hunting for the Leonard Cohen quote, right? Cracks is where the light gets in. It's very important. But I'll make the following because I know you like to make inflammatory comments.
I haven't inflamed you enough.
I don't know of another macroscopic system in science that can be explained so precisely and accurately, you were worried about before, with so few parameters. Just period. I mean, it's absolutely mind-blowing.
That depends on how you count the parameters. I would count lambda, which for you use one number, as at least 60 numbers because
Whatever,
I have
fits
to,
the data. You're
To
putting
be
your
fair,
prior on
wait,
it.
panel. So I invoke my rights as
Yes, please, yeah.
So to be fair to Subir,
No, keep that.
his question was from the CMB alone.
Yes.
Yeah. So then.
And large-scale structure.
Yeah. So you throw in the fact that there are other observables,
Sure,
and in fact that's important, and that's why I asked about how much the total omega m, right?
Yes.
Because there are other information that we have.
And that's all here. For example.
But as a panel now, I want to question the audience here, rather than otherwise this will be a round table and not.
Yeah, sorry.
So
I'll keep that here.
So if you limit yourself with a set of data, why curvature is not included in discussion?
Why did well, simply to limit the number of parameters. You could include curvature.
1, 0, 0, 0.
You could include that. I just wanted to give a proof of principle.
No, I mean.
No, but you know what I'm saying, right? The proof of that people have this statement, and then I was exposed to it at least 3 times in this meeting, that you must have lambda independent of the supernovae because of LCMB and large-scale structure. All I'm saying is, here is something that we may not have seen, that you can actually match that data, and I take on board all of Lyman's warnings that the data is now a lot better, there are other sets of data, but these are the major things. Sorry?
And you're predicting a mass.
And I'm predicting a mass which can be falsified tomorrow by Katrine in Karlsruhe. So, live dangerously, right? That's what I say. So, yes, in fact, that would be interesting. And in fact, I'm watching with great amusement from the sidelines, people now finding a negative mass in fitting data to your lambda CDM model with SDSS and so on. I will not get into that, but it's always funny when that kind of thing happens because you know something is wrong.
I suggest we move on in this way.
Absolutely.
You repeat your question.
Yes.
And then we have a vote in the room.
Okay. So let me say, I'll go back to that first question. Is dark energy established from combining CMB and large-scale structure? That's the question. I've just shown you something. So, physics
Raise
is
your
not...
hand if you are convinced.
Physics does not progress by voting. But,
No, but we just to ask an opinion.
It's irrelevant.
well, I don't know. If you want a vote, do anyone want to say something?
Yeah.
Let's not vote.
No,
Yeah.
no, let's not vote.
But does
I
anyone
was
have a
kidding.
counter statement?
But
Let me put it that way.
more statement about this issue in the room.
Always get a Trump. Yeah, that's why I'm.
Very good point, very good point. But does anyone have anything relevant to say here? We have lots more to discuss, so you can move on. But I just thought I'd use chairman's privilege to get a point in.
So I could
Yeah.
make your sociological statement for you. So one of our common friends who was the co-author on one of the papers you show, Amir Hajian,
Yes.
was a student at IUCA, and his first work was with John Narlikar, a
Yes, I
common
know
late
him,
friend.
yeah.
And of course, as we know, John never actually believed in Big Bang. And then when the first WMAP results came out, what he got Amir to do was to fit a bunch of spots to it with, I don't know, 5 or 6 free parameters. So, and I feel you're doing the same thing.
In what way?
That you hold on to this idea and then you want to just keep inventing things until
This work was done about, well, what year did I say? A long time ago. This is not, this is from 2014, 10 years ago.
Yeah.
Yeah. I'm just showing you that work that was done then disproves the statement that is being made now.
I think to be fair to Subir, he's not inventing something correct.
Yeah, I've been saying this all along.
He's just saying there is more neutrinos.
And yes, I've been saying this from the time when you were at school. So let's
Well, that's what Giant was saying, but I'm saying when new data comes out, then you have to update your point of view.
Yes, yes, of course. I'm quite open to data. I do experiments as well. So I very much respect data. Like I said, speculation is cheap, but facts are sacred. That is the way
But
to look at it.
I would repeat an opinion which was just phrased. It's a lot of freedom to allow for an arbitrary initial potential, or initial spectrum.
No? Why? Do you think that a power law spectrum is the best you can do for a process like inflation, which you have no physical model of, apart from a toy
it is
potential?
Not, but
I
when
mean,
you allow
we don't know the
yourself to
physics of
have
inflation.
Arbitrary one. That's you add a lot.
No,
of
this is not as I
know.
answered to Nyash, I didn't want to take up this thing with my slides, but you can actually generate such
I know.
a spectrum from what is called multiple inflation, where you simply alter the mass of the inflaton within one e-fold, and this dynamics has been studied in great detail by people, and you get these features.
I did it 40 years ago myself.
Yeah, exactly.
No.
So you know that this is not something unnatural. It's not like it is doing a loop and then coming back. Anyway, let's move on. Like was said, I just wanted to make that point.
I start from what you said before. So shall we always have curve during the analysis or not?
That I think sure.
I think it's already time.
In my opinion, is such a fundamental. Even if the data always say is 0, something.
And I would say,
Which is the case, but to say, therefore we set it to 0, just to get a more restrictive.
10 years or 15 years ago, when you first was establishing exact parameters, there was reason to fix one, which seems to be the best determinant. Now data is so good that to allow it to vary, I think it's.
Otherwise, we risk, in a sense, we are adding, we switch
We're
off a
talking
parameter and
about
everything
very
is
high
more restricted.
precision in other parameters. So
It's a matter of how we move forward historically. The simplest thing to have assumed was a flat universe at a time when it looked like that would solve the fine-tuning.
I agree.
But now that we are moving on to more complex arenas, then there is no need to restrict yourself like that. And you don't measure, so the curvature and the Hubble parameter are degenerate in that first peak. So you have to assume one to get the other.
There's a theoretical prior reason
Yeah.
for going
Yeah.
towards,
Yeah.
which is that what is not really that likely is that you have this bowl of either upward going or downward going, very large scale curvature, which involves coherent summation, and yet we have this very strong limit on curvature fluctuations on scales below that. Who ordered that? And so that's really, at some level, the theoretical reason for saying, because of this, that one doesn't seem to be likely. That doesn't mean that it doesn't happen, but it's, you would expect that you would be, and this is actually not more interesting, but it is interesting. You could imagine putting in larger scale features in the curvature that are difficult to really nail, but who knows what they can do with the anomalies? I don't know, actually.
Well, that's one point.
Sorry, wait for the mic.
If the anomalies are physical, and notice I said it, if the anomalies are physical, then that's telling you there's a scale, and I think that makes it harder to justify saying that the curvature scale, that you can't put in the curvature, because that's that scale.
Yes, and let's keep in mind that when you are raising naturalness issues, we are dealing with the biggest naturalness problem in the universe, namely lambda. So, when I say this looks fine-tuned to me, I don't want this solution, if you are doing that to recover something that is even more fine-tuned, then one needs to be, have a perspective on the matter. Anyway, let's move on from this. We might come back to curvature, which I agree with you. So next one is less contentious. It's about back reaction. So Marco, can you turn your chair so you can look back? So for the audience, this is something, I want to just briefly tell you what back reaction is, because people bandy the word around, and I found some nice cartoons from a scientific article, American article by Buchert, where he shows this. So this is the idealized universe that most of us study. The real universe, as you know, today doesn't look like that. It did look like that at the last scattering surface, but today it certainly doesn't look like that. It looks like this. And the problem is that in order to calculate things in the real universe, which has got fluctuations today of order 1, we are still using in many contexts this progression here, whereas we ought to do this one, and clearly the two are not equivalent. So the point is, how do you actually determine what's the mathematical price to be paid in approximating this by something like this?
No, indeed, this is a very good connection with this issue of the curvature, because I like the cartoon.
Yes.
Please note, the audience is not very visible, but the idea of Buchert is precisely that the scale factor is actually the power 1/3 of the volume we live in.
Right.
And then, so going back to the simulation issue, in GR you do exactly that with numerical relativity.
Precisely.
You don't have to invent an averaging scheme, you just compute that volume and take a power 1/3, okay?
Yeah.
In the limit, with the limit of the simulation I presented, we found that this effect on the volume itself is negligible.
Correct.
Okay?
Yeah.
But I agree that there are other possibilities that needs to be tested. But also this is where the curvature issue come back, because if we think what you just said, Dick, about the curvature as a prejudice coming from the initial condition, and that's good. But we don't have enough evidence that there isn't some curvature development between, say, the initial data that we take at last scattering and through the nonlinear evolution. Because, in fact, in this story, there is the part which is back reaction in the sense of possibly affecting the expansion of the universe overall, but there is also a possible effect precisely on the curvature.
Right.
And in fact, then there is also the issue of what really we call the curvature in this sense. Is Glenn disappeared? He had to go. Because Glenn and his collaborator with numerical relativity investigated precisely this issue. I think the title of the paper was something like what curvature really is.
Right. I've got that paper coming up in a minute. So, okay, this was just the cartoon.
Okay.
The point was simply that Buchert's equations are about doing averaging on this time-like surface. But observations are made along our past light cone, and these two things don't commute. This is the real reason why back reaction effects are hard to compute. But let me show that with the toy model, right? Now, I also mentioned here something that some of you, the students, were asking about this Wiltshire's work. So what the timescape model is that it takes another step. It asks how our measurements relate to these volume averaged ones that Marco was just mentioning, right? So his point is that time is running at different speeds according to the local gravitational potential, and this curvature difference between bound systems where galaxies, where space is not expanding, and in between galaxies where space is expanding, this difference is where initially, when initially the perturbations are 10 to the minus 5, these differences are negligible. But he says that they could be large today. And he has a model in which the void fraction today is of order 60% at a redshift of order 1, and he claims that can actually account just from this timescape picture, right? So we will come back to that, but first I want to show you an equation, because I think we all understand things better if you just show a simple equation. So this domain D, over which Marco pointed out that scale factor refers to, the volume, D cube is that V. You have a correction to the usual equations, to the Choudhury equation in this simplified form, and the Friedmann-Lemaitre equation. You have this curve back reaction term. This term is what is called the back reaction, the Q sub D. And this back reaction term, as you might expect, is proportional to the variance of the expansion rate, right? Because the expansion rate reacts to the local energy density. And this quantity is the one that would determine whether this term overcomes this term or not. Because if it does overcome that term, then you can see this A of D. A of D is not the scale factor of the underlying assumed FLRW universe. It is just this A that refers to the D to the volume to the 1/3, right? So it's a notional scale factor. This is just to show that if you in fact had this term dominating over that term, then A double dot would look like it was accelerating, right? So this has got nothing to do with real observations or whatever. It's just to illustrate that you could have additional terms in the Friedmann equation that mimic the effect of lambda, right? So in fact, as it says here, you can mimic it if this QD is, this quantity is like a lambda effective. Yeah.
So when you say quantities averaged over domain D,
Yeah.
you don't actually do that in observation just here. Do you mean that observations that are sensitive to quantities that would be interpreted as quantities?
That's right, yeah. This is just a theoretical theory showing that I'm unable to, I have some corrugated plane here, and at a constant time hyperslice, I average over a domain D, and then when I write down what the dynamical equation is. Huh?
This is these equations for the background?
Yes, this for the.
Maybe we could discuss perturbations too.
So he takes the.
No,
No, but if you were to discuss perturbations too, on top of this perceived background, I'm
Well,
asking.
He's
in
asking
a sense,
precisely for the
you
back.
have to think the other way around.
It's
In a
the other way
sense-
around, yeah.
In a sense, this is after taking into account all non-linearity of the perturbation, of,
Right,
the
right.
real universe. There's no separation between background.
Yeah, yeah.
So there will, in that sense, there wouldn't be a,
Because
so
in
much
general
of a
relativity, there is no
conflict there.
separation between background and perturbations. Sorry, Ramesh? Yeah.
Yes, sir. I was just, with respect also yesterday's discussion, I just pulled up the paper by Giblin, Mertens, and Starkman.
I'm going to discuss that in the next slide. Can you just wait? We'll come to that. Yeah. Thank you. I'll ask you for a comment.
Right. So what I was saying before,
Yeah.
thanks for pulling up the
Yeah.
equations,
Yeah.
is that in addition to Q, which, so now you can, just to connect to your
Yeah.
question, yeah, what I would say, this is a scheme, this is a theoretical averaging scheme, right? Then what I was saying is that if you can model the full relativistic universe with all the inhomogeneities, in whatever way you want. I did that with the simple but very big inhomogeneity. Then you have a domain of integration, which is your simulation box.
That is this
and
D.
And then you can measure that AD without needing this scheme. But you can then compute. So the second equation is
Yes,
a
yes.
Friedmann equation, right? So
Yeah.
from that you can define omega parameters, including omega D, omega for Q, and that's what I've shown to be small. But what I was saying before, this equation also contained that term R, which is a curvature term.
Yes.
Okay,
This
and
one.
that one we didn't compute it, to be
Yes.
honest.
Yeah. So this you are one, if that is non-trivial.
And
Yeah.
it could be, in fact, maybe, so if you ask my opinion, or I will offer my opinion, is I'm pretty convinced, I agree with what we discussed, that maybe some more theoretical work with numerical relativity will be done to test this framework of back reaction even more.
Yes.
But in particular, I believe that maybe back reaction is going to not to be there, but
Yes.
maybe a curvature effect
Could be there.
Can
yeah.
be there. Yeah.
Well, so that is precisely the point. Most of us who don't actually work on this and only know that there is a vigorous debate going on between, Green and Wald and Booker et al., who say Green and Wald actually assumed FLRW, so therefore their conclusion is a bit circular and so on. So I don't want to get into that or take sides. I'm not sufficiently expert in the matter.
In fact, to connect, just to finish, just to connect with what Dick was saying.
Yes.
So, in my opinion, following from what I said, if tomorrow we measure omega curvature, 10 to the minus 2, right?
Which is quite possible.
Some people will immediately jump and say, "Oh, that kills inflation." I would disagree because of this reason. Because it could be generated, and the universe could be perfectly.
That actually connects also to timescape. Same thing. Wilshire says this. So actually, that's what I want to come to now. So, question is it possible through relativistic simulations of large-scale structure formation and constructing light cones in those simulations and looking at observables like luminosity distance, angular diameter distance to determine if these back reaction effects are actually important, right? So I'm sorry, I thought Asim would be here.
Can you go back to the previous slide?
Sure.
So I mean, when that paper came out in the year 2000, I was a graduate student, and it's very attractive, very nice. I just said, okay, what is this Q? And we could just plug in from perturbation theory to second order. And it turns out those first term, and I mean, it looks like these are reasonable terms, but you can use Gauss's law and show that the first term cancels the second term and it's 0. And then you only end up with...
Sorry, you mean this term cancels this term?
No, the QD term. QD.
Oh, this term cancels this term? Okay.
The first two terms cancel the last term, basically.
Why should they do that? Because the average of the variance is not the variance of the average.
Because they're both functions of the velocity. So one is divergence of velocity, the other is the terrestrial part. So you could use Gauss's law and show that one basically up to the surface term, the two cancel each other. And so the maximum you could get is for surface terms, and that's the 10 to the minus 4. And that was 2000. I stopped working on it, and then people kept doing this, and whoever did a rigorous calculation got 10 to the minus 4. But I think this is something that you could do on the back of an envelope. It is 10 to the minus 4.
Saying if the flow is curl-free, then you have a connection between these two.
Even if, well,
it has to be divergence.
This assumed is curl-free, but if you do put in curl, it's still
valid.
It's a surface term, yeah. So I'm saying no matter how you calculate it, if you do it consistently, it's 10 to the minus 4.
That means don't go
however,
yes.
However, that's a perturbative calculation, and the whole point is that this is a non-perturbative
Thank you,
effect. In fact, in my plot, you have seen that there is a big jump between the perturbative second-order prediction and the full calculation.
Yep, I agree.
Just make a quick comment on this, and I will just say J3. And I'll bet nobody here but me knows what J3 is.
It's the integral of the...
You would probably know. J3 was the original reason that we put bias in when we were normalizing delta T over T. And so that's
Is
where
that
bias
integral,
came from.
right?
J3 is basically the integral of the correlation function starting, and it was done with galaxies. And I'm going to invoke authority, one James Peebles.
Yes.
He, and that's why we used it. It then became delta n over n squared, thus sigma 8. But what am I talking about? What I'm talking about is that you do an RG flow running of that quantity, and what you find is that it damps away. So the only way that this stuff can work is by high-frequency spatial things that are just generally not taken into account, and where have they come from? And we don't think they're there. You would have to prove that they're there, but it isn't large-scale structure stuff, because we know that that's not the case, although I must say it's a really good project to do a J3 flow again after all this time, because you could sit on all sorts of objects and do it, and it becomes somewhat local, because, I mean, the basic point is that clustering is compensated. And so if you compensate the clustering, then eventually you get to no extra terms. But if you're saying that it's not compensated, then you'll be right that there's a correction.
Okay.
But, you know, and you could say that's model dependent, and it is, but it's the situation that is at the heart of all of our thinking about what arises from the early universe, that you will get a situation where it, as you run to K, G equals 0, which is basically the volume average. I mean, really what we're talking about here is the relationship between the ergodic theorem for the universe, of which there is no evidence that it doesn't work, but maybe it's not strong enough right now for your...
Yeah, actually, I was going to go on to an argument that is meant to be analytic and should cover that, but you had
No,
to
just,
cover first.
it's too bad Glenn left because I think there was some discussion about the results of numerics trying to address this question too.
That's what is on my next slide, but I see Glenn has gone, but Marco is here, he can comment on it. Also, I wanted to highlight a paper by... Yeah.
To give the J3, I mean, it's going to run towards uniformity. So it's guaranteed to do that. So you're not going to find it from the sims because you set it up in such a way that you didn't get it. You would have to come up with a model that has asymptotic breaking of the overall integral going to uniformity at very large scales. And it's all just, it really is just an RG flow problem. But RG flows are not trivial when you have a light cone.
Well, so the question is whether this extends to the non-perturbative level, and this paper by Asim and T.P. Singh, who was the supervisor, it claimed to solve it in the rigorous Kalatnikov formalism to show that back reaction could not be significant. Do you know this paper, Marco? Yeah? Okay.
He comes back.
And yet comes back, yeah. So I thought he might be, yeah, so he might be here to say this himself. So I did ask him. Of course, there were caveats in that argument. The caveat was that peculiar velocity should not be, quote, large, right? So I asked him, what is large? And this is what I really would have liked to have a discussion on, because they wrote this paper, 2008, some years ago. And at that time, everyone believed that peculiar velocities were small, according to what you expect in ΛCDM. They fall off and they average out, etc. And I think the situation has, as has also happened with other things, changed since then. And it's time to revisit some of the consequences of the assumptions, or rather, the consequences of the new data on the assumptions that were made. But since he's not here, let me move on to this relativistic simulation. So as Glenn mentioned, there were 2 papers published back-to-back in PRL, one by Marco and his student, and the other by Glenn and his students, and Giblin. And both of them concluded that, well, in different ways, I should not really lump you together, they're completely independent studies, but they basically concluded that back reaction effects, Glenn's made a strong statement. What does it say? The universe, well, you can't read it from the back, so I'll read it out. The universe that emerges exhibits an average FLRW behavior. It also exhibits locally inhomogeneous expansion beyond that expected in linear perturbation theory. But overall, they did not say that this would change anything drastically. And the same last line appears here. The magnitude of these back reaction effects remains very small for relatively large perturbations, right? However, using a different method, the Devolution code, this Adamek et al., Ruth Durer's group, hedge their bets, and they say in their abstract, the back reaction from structure can differ very much depending on the slicing of space-time that you choose to average over. So for example, you may not get anything for the time-like, constant time-like surface, but you might get one on a different gauge. I don't have that abstract here. Would you like to comment on this, Marco, since you're the only representative of the school that says back reaction is unimportant?
So, I don't remember this particular paper by Julian, but in general, that group also concluded, in fact, I think it was after this paper.
A subsequent paper, yeah.
That they have a paper in Nature, which was like a sum up of what the investigation they have done. And just to be clear, this was done by a code developed by Julian Adamek,
right.
Which is G-evolution.
That's a code, yeah.
Which is another code which is relativistic enough for the type of problem that we are talking about.
But they can
here.
go past shell crossing. This was their
Yeah, it's an
this was their
embodied code. It's an
USP.
embodied,
Yeah.
it's an embodied, like
Yeah.
the code by the group by Glenn.
Yes.
And they also concluded that back reaction is essentially negligible. Yeah.
Yeah.
The point they are making here is that one has to be careful with gauges, and yes,
Okay.
I mean, but we know that. I mean, if you can, the gauge effects are part of life for people dealing with relativistic theory. Even if you have a perfect Robertson worker, if you write in funny coordinates, it will be very inhomogeneous. So this is just stating the same way, the same thing about the result of a simulation.
Very good. I've got you where I want you because I wanted you to say that so that I prepared for the next slide.
You're manipulating me.
Yes, I don't know. Because the next slide is to do with the fact that these guys, this Aramek et al.,
Are
when
you
they...
just talking to each other?
Sorry? No, okay. No, but sorry, please, you had a comment? I didn't miss. I do apologize. Please go ahead.
No, I thought I was always taught that observables are gauge independent.
Yes, indeed.
And if you choose a gauge which is inconvenient and poorly splits in background and perturbation, that's your problem. Choose another one.
No, the time hypersurface is a different choice. The gauge is trivial. It's the time hypersurface.
The constant
you do
time,
these
yeah.
measurements on.
Yeah.
That's the issue. And if you shift time hypersurface, you can obviously do a huge amount of damage because what you're doing is you're putting into the time hypersurface what is in effect dynamics. And so therefore, that's the critical thing, and it's always been the critical thing, and everybody overuses the word gauge.
Well, because in numerical relativity, the word gauge refers to the slicing, right? You have a lapse and shift, and that's what you define as gauge.
But that is not gauge,
In
that's
that context,
the hypersurface choice for time.
Yeah. It's jargon from different communities that sometimes can be confusing.
Well,
Dick, our observables are local here. We're getting photons here, we're getting other radiation here. What you measure cannot be gauge dependent.
Correct.
Choice of a
No physical quantity should be.
Nothing.
Yeah, agree.
We
Agree
agree.
completely. By the way, if anyone has any comment at any time, please raise your hand. I don't want to exclude anyone from this.
following reason, you have to connect here, there, and everywhere, all these things
Yes, yes,
together.
everywhere.
And that is the issue of building a coherent time. And coherent time, we should all understand, is a miracle in general relativity, and it's probably not even true. It's just that that's what we enforce, and that's because we are classically bound in our thinking.
Yeah.
But the fact is, the way it works is that you have your time clocks here, you have the time clocks here, and the brilliance of one Albert Einstein was to say you have to synchronize your clocks in order to say what's going to happen and relate things together. But then what we're talking about here is that you can corrugate that surface, and then therefore you can make patterns look differently. But that is a total construction that we do, and everybody takes it for granted because everybody likes a C2 differential manifold as opposed to one that might have a lot more complication.
But you cannot get photons hitting your eye different by doing.
Can't do what?
You cannot get photons hitting your eye.
Yeah, but
different.
But when Elon Musk is on Mars, is he going to get it at the same time as you?
Well,
You have to do that correlation.
Anyway, let's move on, please, because we haven't heard from the other panelists yet, and I do want to get on to them. Yeah.
No, actually, synchronizing is an amazingly complex
Okay.
phenomenon.
So the point I want to raise, which I would like the other people to come in on, is this calculation that they did, that you referred to, Marco, where they say that when they construct a light cone and they don't see any back reaction effect, they picked a typical halo in a simulation, right? Now, the question I want to ask, and this is open to everyone to comment on, not just Dick, is the real universe looks like this, okay? This is our local volume as mapped by, this is from Cosmic Flows 3, I think 4, it looks almost similar. We are at the center, we are flowing toward Shapley, and this is the peculiar velocity field that Rick discussed. The question is, we make all these assumptions when we analyze data. So some people assume it to be exactly homogeneous, that's clearly wrong. we discussed back reaction, which is one way of trying to take that into account statistically. But what about this assumption that we are a typical observer? I mean, does it not matter whether we are in a overdensity or a void, etc.? And of course, this is considered by some people in some contexts, but I'm not, what I'm saying is that this is not something that has penetrated to the point that, for example, Adamek et al. Did not consider this to be a relevant issue when they constructed their past light cone. The point being that our neighborhood is highly unusual, and I'll show you why very quickly, because if we are actually in a lambda CDM perturbed universe and we are flowing towards here because something is pulling us, then that velocity should fall off as 1 over r, because we should then converge to the frame in which the universe is isotropic. And this is the plot that shows our local bulk flow averaged in increasing volumes. These are the radius of the top hat smoothing filter. And this is all the data until 2021. This was all the data, and it was all fairly consistent with the purple line, which is the expectation from lambda CDM. If you take the matter power spectrum from galaxy surveys, you integrate over that with the right filter, and this is what you get. It's pretty consistent, although there were already a few discrete points at the limits, but the error bars were very large. Now, what has happened since then is that there was this point from SDSS, and then there is the points from Cosmic Flows 4, which Rick Watkins told us about, which are up here, right? And as they say in their paper, these points are highly discrepant with the standard model, highly meaning at some 4 point something sigma, they have about 10 to the minus 4% probability of occurring. So if I now ask, what sort of environment in that volume there, here, would be typical in how often they would occur in a lambda CDM simulation, the answer is it is actually extremely rare. Okay? If you look at the dark sky simulation as we did, we find it very hard to find a volume like that. So this is something that needs to be factored into these statements about how likely back reaction effects are, because you don't pick a typical halo, you pick a highly unusual location in the universe, such as we are in, and this is the only place. We're talking about photons entering our eyes. We can't go to some other galaxy and see if it's the same photons. We are only here. And so there is a cosmic variance effect which is to do primarily with our position in this web, and this is something that we need to take into account. And this is also the point that relates to what Asim and TP Singh's paper. This is already a few hundred kilometers per second. We were talking yesterday, and he said if it got to 1,000 kilometers per second, then his argument clearly fails, right? I think that's a very fuzzy answer. It can't be right and wrong. Yeah, he said if it is 10 to the minus 3, then he assumed it to be much smaller.
No, I mean the effective, it would be a square of that. So if it's 1,000, it would be 10 to the minus 4. I don't know. So you all the back reaction effects are a square of velocity.
Okay.
So I don't think 1,000 makes a huge difference.
So at what point would it be? So it's an analytic argument. So presumably,
if it's half of the speed of light, then it would be.
That we agree.
Yeah.
But
I think that's
but below that also, at some point, it would be relevant.
I mean,
yeah.
Marco had the 0.1. You had some. When does back reaction become important?
Okay.
Yeah.
Since Asim is not here, unfortunately, I had hoped he might be able to resolve this.
Unrealistically large.
Anyway, I think we have had enough of back reaction, but I think people like to go away with some message in their head. My personal feeling is that there is still work to be done. It is not a closed problem. It has not been established either analytically or using simulations that people, observers such as us, living in the environment that we do, which is clearly unusual, as revealed by the bulk flow, that we would necessarily not see any back reaction effects on our past light cone.
So, in fact, okay, if I can make a last comment on
Yeah.
this. The type of back reaction that I've been talking about is really the dynamical part related to the evolution, right? But there is a connected but separate back reaction, which is really how the inhomogeneous universe affects what we see. And that, I think, needs more
Okay.
work,
Yeah.
including going back to this issue of the curvature, because if there is highly curved universe that is developed from the initial data through nonlinearity at small scales,
Yes.
then that will I don't think that is never going to really affect dark energy issue. It's really more like, however, maybe it's going to affect our observation. Okay. In fact, that the picture you have shown about the lensing of CMB. Right. Can you remind us what's the scale of those? In your picture, there was like a black blobs, let's say. What was the typical scale of those? Of almost the same size.
Yeah.
In fact, I wanted to ask
degree-ish.
why they are almost the same size.
Yeah, they're sort of degree-ish.
Degree.
Of the order.
That's
yeah.
the scale of
that's
the
the-
experiment.
Okay.
That's the peak of the power spectrum,
Okay,
the
the
lensing
peak of
power
the-
spectrum.
The matter power spectrum.
Yeah.
No, the lensing power spectrum.
Of the lensing.
Ramesh?
So if I may be allowed to add what you said, how the inhomogeneities affect our observations. This is what I was, and that is specifically what the fitting problem is. The fitting problem in cosmology is literally about how the data interpretation is affected by the inhomogeneities. And we have demonstrated over 2 papers and a couple of reviews which go into even more detail. All the code is public. You can reproduce every plot. That all the evidence for acceleration in the supernova data comes after correcting for peculiar velocities, and peculiar velocities are an aspect of inhomogeneity. They arise because inhomogeneities come about, and the corrections are done according to methods that have in some sense presciently been discussed in the fitting problem in cosmology. So this has led me to write a long argument. So so I do think it is it's important that the entirety of dark energy as observed from supernova data is due to inhomogeneity.
Okay, I think you should move on because you could spend a long time on this because we haven't heard yet from the other panelists. Now, I'm not going to guide the discussion any further. Please, would you like to say something about what your response to this meeting was and any particular issue that you would like to bring up for discussion?
Well, this was really, really stimulating.
Yeah.
I had a few observations
Yeah,
which, as a bit more classical astrophysicist in the meeting, I thought I could make. So one was,
Can you point the mic towards your mouth? It's
Yeah.
okay. Yeah, thanks.
So I thought, I guess, one observation was that there seems to be a hierarchy of problems that people, a hierarchy of discomforts that people have about lambda CDM, which I thought was interesting. For instance, there is at the very basic level the tensions within the lambda CDM, and then there is a concern that the lambda CDM itself might not be a valid interpretation of data. And then at the third level, perhaps, was that the lambda CDM was not being computed correctly. And that's where the back reaction and so on came up. And I wondered if this type of a hierarchical view of this subject is a useful way of tackling these problems. So for instance, coming from my point on the landscape, the tensions on within the lambda CDM, I was a bit surprised that the systematics in the data were never mentioned in the whole week, which was quite interesting. Or perhaps you did. In which case, they were only mentioned on one of the 5 days.
Yeah.
Sorry.
They're mentioned by serious experimenters.
And then I guess a related point was what I tried to make, which is there a serious issue between the astrophysics cosmology divide? Can astrophysics fake some of the tensions in lambda CDM? That was one of the points that ran through my mind through the week. I have a few other observations which I'm happy to make later if we have
So
time.
we'll come back to this. If someone wants to comment on what Girish just said? No? All right, let's go to Changbom. Please, get the microphone.
Well, I hear about lambda CDM being talked. Well, I'd like to emphasize that flat lambda CDM has been ruled out. Okay? So it's been...
Well, he showed with DESI data.
I showed in my... and also it's confirmed by subsequent observation, by independently. Okay, so that... but the issue I want to ask to all the participants is whether or not, at this point, where people are starting to measure actual value of W, is it desirable to combine late-time universe data with CMB? Because that's the point where we start to see difference between my calculation and other member of DESI consortiums. So as soon as we combine low redshift data from Alcopacinic test and BAO and supernova, they are all consistent with each other statistically. And then as soon as we combine the joint constraint from low redshift probes with CMB, then the dark energy model suddenly jumps to indicate that there is phantom divide crossing. So, and same thing happened a long time ago in late 1980s and early 19, when we make the transition from SCDM to low omega matter CDM. Okay, I guess you all remember this standard CDM power spectrum was able to fit the small scale density fluctuation. Okay. And in 1992, is actually February 1992, there are two papers published. One is the COVID DMR detected the delta T of T on 10-degree scale, which predicts 4 to 5 times higher power on CMB scale, okay? Which means the density fluctuation is about twice higher there. So this power spectrum was not able to fit small scale and large scale simultaneously. And at that time, the only way to vary cosmology is just change the amplitude up and down. So if we just change sigma 8 to try to fit both, then we end up getting some intermediate sigma, which is wrong. Okay, so we had to introduce, make the cosmological model more flexible so that it can also move horizontally. Okay, so we move it to large scale, and then move up, and then we are able to fit both CMB and galaxy large structure scale. And to do that, we had to introduce one more parameter, which now is lambda, or dark energy.
There are two other ways. This was in Josel's review. One was tilted TCDM, you remember, tilting the spectrum, and the other was CHDM, cold plus hot dark matter, which I showed an example of. That would also suppress the power on small scales
no, it's not,
by different mechanisms.
Well, it's not a matter of suppressing the small scale power spectrum. The small scale power spectrum was able to be fit by this function already, but it just couldn't fit both scale.
The amplitude was wrong, like you said. If you couldn't fit both the Kobe normalization and the two-point correlation function of galaxies on small scales.
So that's why the model.
The shape, shape was the problem.
Yes, so that's what I'm saying, that there are other alternatives to shifting it to the left, which is
so now the models are much more complicated than that. When we had only one pre-parameter, the amplitude, and now we have many other options. But still, by nature, the problem is similar. Okay, so I don't think at this stage where we find many discrepancy between low redshift measurement and early universe measurement, we should not combine low redshift constraints with the constraints from CMB, and unless we expand our pool of cosmological models.
That could be for there could be other rationales also for that. So CMB, for example, the universe is clearly pretty well described by FLRW at the CMB epoch. It's very smooth, small fluctuations. At the epochs where you're measuring galaxies, in spite of the fact that DESI is continuing to use a FLRW metric.
And,
you know,
and late time,
that also
Dark
has
Energy.
been contradicted at more than 5 sigma. So, you know, it's a matter of what data you preferentially choose to believe, isn't it? So in principle, I agree with you that I think that these are very different domains of redshift. The description of the underlying cosmology could be different from one to the other, and we don't as yet have something like the renormalization group which would connect phenomena at different scales at different epochs in a smooth way. We are using one size fits all, right? So, I mean, I take your point, but I don't know if, and I just find it odd that DESI has got this beautiful data and they start by saying we assume the FLRW universe. They don't even test whether this is borne out by their own data. Anyway, sorry, you triggered me. I shouldn't say. Yeah, you haven't spoken. Maria-Teresa, please.
Okay, yes, yeah. I quietly agree by the fact that we have to rethink of we are going to build our observable, our low redshift, high redshift. As a poor astrometrist that is dealing with the general relativity, I think that it's important to rethink the context where the problem rises. So, and especially if we improve inaccuracies. And I think that it's important, the curvature could be an important effect to take into account, and different way because it depends on what kind of geometry that you are going to use to describe your phenomena. And one thing that we have not maybe really discussed is the source of the curvature. And for example, the role of the black hole in formation, in the galaxy formation, of the role of the black hole in high redshift, so the seeds of black hole, could be this relevant because we don't know. We start to understand the physics of black holes. So we have black hole in our garden. We discovered very close black holes. So they should do something, at least, and the head should have a physical role somewhere, you know? And I think there is, and to compare what we observe, we measure locally, to what we observe in distant universe, we should be very careful. For example, for distance for supernova, I think that really model dependent. They say this independent, but it's really model dependent. You have to redefine your distance according to a local observer, your local workflow. I see that the geometrical definition of the distance is not taking into account in the empirical formula.
Right.
So this is my...
Thank you. Yes, Rick, you have a comment?
I was just going to ask the panel, from Christos and from your talk and from several other talks, it sounds like, I mean, one could take away the view that this averaging that we do and using the FLRW background just doesn't work at all, that the universe is completely different than we're getting from that. That maybe we don't need dark matter.
Can you hold the mic closer?
Oh, sorry. That we don't need dark matter at all, that we don't need a cosmological constant. So what's your thought on that? Is there some way in which we could be completely messing up by doing this averaging? Or, I mean, it seems to be successful. That's the weird thing, at least until now.
But actually, I don't think that the point is if dark matter exists or not exists. So we see the effect of dark matter. So we are trying to explain the effect of dark matter. If we say there exists dark matter, we assume that matter is an entity. So, but we are actually, what we observe is the effect of dark matter, the effect of dark energy, or not. So, so we are looking to look for how to explain such a phenomena. And of course, it's very important to have many models to compare to test the model, because from my point of view, it's very important to exploit our local universe, because of course, if you, for example, MOND, as was said, it has not in the solar system cannot explain the deflection. In certain way, you have to rule out MOND. So it's very important to keep the comparison between different theoretical models, just not purely one idea, one mathematical model. So I will be very careful to say does not exist dark matter. Yes, I prefer to say I'm going to explain the effect of dark matter, what we are going to we observe in the universe, but.
So maybe one way to say it would just be that we're going to learn a lot more how rich our theory is, that we're missing some of the richness now by not.
Yes, we are missing. General relativity is a complex theory. We are missing more mathematics. There is a lot of mathematics to do with Einstein equation. We know a few solutions of Einstein equation, but it's not only that. It's how we apply the protocol of measurement of general relativity, which not just to find the exact solution. That we have to define accordingly a new kinematics, maybe. New dynamics, I don't know, but instead of to try to change general relativity or to extend general relativity, maybe, but even in this case, at least we do everything in the background of general relativity.
I would like to add while I have the mic, that I think we do make the mistake of just thinking of a bulk flow as being a dipole through a volume, and as I showed in my talk, it is much more complicated than that. That it's not just that the whole volume is flowing in one direction.
Yes.
That it's very spatially inhomogeneous.
Thank you. Yeah. Yes? Microphone, please.
I also have a question that comes from Christos' talk yesterday. And in that he said there's a bulk flow contraction that's happening on the megaparsec scale that is causing us to see the expansion as accelerating. But shouldn't this also result in us seeing a local blue shift in the area where the bulk flow is contracting? And if yes, have you observed such a thing?
We do see a directionality in the deceleration parameter in that direction. Not on megaparsec, but hundreds of megaparsecs.
So with very nearby galaxies like Andromeda, you do see that they're coming towards us, not far away. So that is true on a very much smaller scale. But the contraction of the bulk flow is still assuming there is an underlying Hubble expansion, and it's on top of that, and it's much smaller than that. So it doesn't actually lead to a blue shift within the entire bulk flow region. It just means that the rate at which things are redshifting has an anisotropic component on top of the Hubble expansion component.
Because at 100 megaparsec, the Hubble flow is 70 times 100, 7,000 kilometers per second, right? And these velocities are a few hundred, much smaller. So it's a perturbation on top. Anyway, thanks. We did want some questions from the audience. But I think we have exhausted the panel. Oh, sorry. Please, Girish, go ahead.
If it's okay, can I ask you a question, Subir? I was actually wondering throughout the week what the sort of highest leverage next step might be for this problem. Is it the acquisition of better quality data? Is it the performance of better quality simulations? What? And I don't know if...
which problem?
I guess revisiting cosmology problem. I guess the problem that there is no consensus in this one room on lambda CDM being the one correct cosmological model. Or is it just a sociological problem which vanishes when you step out of this room?
When you either believe the DESI data or you don't. If you believe the DESI data, and we've seen what the consequences are. So that breaks lambda CDM in the classic sense where lambda is uniform. That's just the way it is. I don't see that that's a real breakthrough in terms of the setting of our models. There was never indication of why it should be a uniform lambda. In fact, I think it's ludicrous, the people that have a religious belief in uniform lambda. It may be that the slope is so small, the gradients of lambda are so small that there isn't a lot of motion associated with it. But of course, the quintessence story, let's recall what happens there. The wave structure of the quintessence flows out by collisionless damping when it comes into the horizon, and that's why you don't see structure in the lambda story if it's based upon a quintessence thing. but that depends upon the details of the potential. So there's all sorts of ingredients that still fit within our kind of standard framework. And what we're trying to do is to draw that information out. Now, what I have been trying to do now, which I actually did succeed in doing, was to demonstrate to myself that, in fact, what I was saying about the J3 problem, which is not a problem, you can easily show that the effects that everybody's worried about the fluctuations go away if you do an RG flow up to a large enough radius. Because what happens is that the fluctuations are associated that are going to enter into all these modifications. They're all of the form of basically a delta K, where K is a wave number. But the wave numbers are gradients. You express it, and what you get is an integral over what is in effect a grad of e to the minus, I love my entropies, e to the minus entropy, but it's like number. And because of the grad, when you flow out, it goes away. But every place that's local, you have to take into account that there is a density structure, even with a reasonably large scale flow, which does not get rid of that effect. But every time anybody is doing an analysis, they take that into account because they're dealing with the objects that we see. So I don't really see that there's a huge problem, nor a methodological problem in what people have done. So I actually don't fully understand what the conversation is about, except for one thing. If the vacuum somehow decides that these K fluctuations don't go away, but it wouldn't be just from clustering on the scales that everybody's worried about it. It would be from some kind of short distance thing rising up from below and capturing us with something that goes to uniformity. And let me make one other comment, which I don't think is that much appreciated. Who ordered that the vacuum energy density would be not dependent upon constrained fields? What am I saying? That's called an effective potential. Every effective potential is exactly that. It is rho vacuum as a function of a phi c. When we do the early universe calculations, that's what we're doing. And yet, some very respectable particle physicists who I know will not even entertain the possibility that you can have the same thing happening around us, which is that the vacuum energy will be a function of very long wavelength fields, and that changes the dynamics. Now that, to me, is the much more interesting way to express the problems we're dealing with, and it gets back to the quintessence issue.
I can actually give you a very well-motivated particle physics example where things change.
Can you give the mic?
And the thing is, this surprised me. So this is something I was working on with Yashar Akrami, and we never published it. But if you think that we live in higher dimensions, so this is a string theorist sort of a perspective. If you live in higher dimensions and you have a higher dimensional gauge field and you compactify it, and then what we view as radiation is the compactification of a six-dimensional gauge field. Now that thing is going to talk to the background. And so you're going to get a coupling to whatever it is that's stabilizing your potential, and so you get a potential that basically tracks temperature, right, as the dominant matter content. So this thing really naturally exists within a model. So this is indeed a possibility. It could vary in time. And I think what people have stopped doing is they just haven't worked out consistent truncation. They've just sort of written down things in 4D and said things like, you can't couple things to, but it can be done.
Sure. I'm afraid we can't go into that now because you're supposed to clear the room. So, Rick, you had a comment?
Yeah, I just want to make a couple
quickly.
really quick comments. One to Dick is that I think you can believe the DESI data without believing that it's broken lambda. So just a comment. But two, I think the answer to the question...
Without Chung Bomb beating you up.
Well, but I think the answer to the panelist's question is that we're on the edge of a huge amount of data that's going to come into our system in the next decade or so. So if we were to have this meeting in 10 years,
yes.
if we were to fast forward to 10 years from now, we would have a completely different set of problems.
I agree with
I think
that,
all
yeah.
the problems we're talking about this week are going to be resolved.
I actually have a last slide, which I think everyone here will agree with. You cannot not agree with it. And this is something which is on the gravestone of David Hilbert. And it says, we must know, we will know. So come back in 10 years and we shall see if you are able to live up to what David Hilbert believed. He said that in a radio address in 1930. We are nearly a century ahead.
Interpreted in many different ways, so I have already got 5 different interpretations.
Anyway, never mind. Yeah, exactly. We have, see, cosmology audience, we have 5 different interpretations of that. But exactly, that's what I'm saying. So we'll hold it in 5 years. But meanwhile, I really appreciate that all of you stayed through this very interesting discussion. I do wish we had time to go more, especially into the aspects that Subodh brought up, but that would really take us past our time. So thank you very much. Thanks to the panel, thanks to the audience, thanks to the organizers. Yeah. Please.
So thanks all, and I'll not take a lot of time, but just wanted to take this moment to thank a lot of local organizers along with the SOC. So first of all, a big thanks to all the speakers, all the chairs, all the moderators. I think that made this conference a great success. Of course, thanks Subir for taking this initiative along with Tarun, Prava, Ramesh, Mayuri. Yes. Yes, so SOC, I think some of us are here. Prava, please. Ramesh.
We want this moment to be recorded for history. Somebody take a picture, please.
We can compare after 5 years. Yeah.
Yes. Mayuri is in France and Tarun is in a meeting, but
Yes.
we'll substitute for them.
Everybody smile and say lambda.
Thank you.
Yeah, moving on to the LOC, lot of background work has been done here, and I just want to give a big shout out to all the LOC members, some of which are here. So Aritra Mandal, Arunima, please come. Yeah, please. All the beautiful designs of all your conference kits has been done by her along with the website. Dipayan, not here. He's done a lot of work here. Sachin Belwadi, keeping all the accommodation and every other arrangements. Some of you must have interacted with Subbu. He's our executive assistant. Vaishali, a PhD student, doing a lot of work for this conference. So along with it, we had a lot of administrative support. So Rahul, keeping literally an eye on everything going on in the conference through your camera. Transport, Manjunath, who's not here, but he's taken care, I think, of a lot of logistics related to the transport. Vani, Vijay, and Bhujangarao, along with them, to make your logistics much easier. And of course, a lot of it has been facilitated by Tarun and the administrative officer, so big thanks to them. A lot of visiting students here, unsung heroes, are all here, so I'd really request you to all please come here. Meet, right here. Hardik, Devarshi, Akshank, please. All of you here. Arunima, Rahul, Vaishali, please. No, here.
Don't be shy, please come.
Please come in. Yeah, no. I'm not part of this, so you please.
Actually, we should move you over and have, we must know, we will know.
Oh, of course, great. Yes.
That will be a good backdrop. Come on the stage.
So let's try that. So get in front. We can see what we
Go ahead, please. Just behind the table. Yeah.
Yeah, do what you want, but don't hide.
No, it's in German on the top, so it's okay.
Yeah, don't, well, yeah, I know, but, okay. Don't hide, don't hide yourself.
Well, anybody knows German on the top?
Thanks a lot. And we disperse now. People who had signed up for the museum visit, we start at 4:30. And there is tea and coffee outside, so we'll proceed there.